So this is continuing with chapter 19, and I'm going to focus on a couple different ways of calculating what we call delta G, standard free energy change. The change of free energy if reactants and products are in the standard state. So we are always assuming that we're at 25 degrees Celsius in 1 atmosphere. And so when we look at this equation, please note that that degree sign is going to be something that we keep track of. And one other thing, if I didn't mention it before, the temperature needs to be in Kelvin. So one way you could do delta G calculations is by finding the delta H and finding the delta S and plugging it into this equation. So that's the first one I'm going to show you here. So here's my equation. Finding delta G at the standard conditions. Is this reaction spontaneous? So we want to know if the delta G is positive or negative. That's going to answer that question for us. So one way you're going to see it is I'm going to give you data for your delta H and your S. And please keep note of the actual states of matter. Of the units. This is in kilojoules, this is in joules. So I'm going to pause the video and then come back here in a moment. All right, so I found my delta H is negative 112 kilojoules and my delta S is negative 147 joules per Kelvin. Again, products minus reactants is how you do all of these calculations, taking into effect, of course, the balanced chemical equation. So let's plug this into delta G. So delta G is equal to negative 112 kilojoules minus, now my temperature at standard conditions is always going to be the same, 298 Kelvin. And then my unit of S, since I'm doing this in kilojoules, I have to convert this to kilojoules, or I can convert this to joules, and whatever you want to do. So this is going to be a negative 0.147 kilojoules per Kelvin. Okay, so just keep that in mind. I don't care how you do it, just as long as you keep in mind that this is in kilojoules, this is in joules. So this becomes essentially positive over here, but it's not big enough to worry too much. So it ends up negative 68.19 kilojoules. And there's some issues with some rounding there, here or there. But it does come out to be negative. So you're not done. You need to say, yes, it is spontaneous to get full credit on that. Okay. So that's one way of doing what we call a delta G calculation, is finding the delta H and finding the delta S and plugging it into the equation. Second way is going to be this next one. But just to kind of confirm that we've made this statement before, delta G is a state function, so it's independent of path. So it doesn't matter how I calculate delta G, it will always come out to be the same value if it's the same equation. So remember, H, S, and G are all state functions. They are a capital letter. So do you remember the things that we talked about in first semester that are not state functions? Those are little q and w. Okay, so if it has a lowercase letter, it's considered to be not a state function. So H, S, and G are all state functions. So that means I could calculate delta G any which way I want. So it's going to depend upon the data that I'm giving you. So a second way, so if you want to put a 2 next to it, is something like Hess's law. So this is like Hess's law. Okay. So if I flip reactions from Hess's law, I'm going to change the sign. And if I double the reaction or do anything to the reaction, I'm going to double the delta H. In this case, it's going to be the delta G. So here is my equation that I want to find the delta G for. Again, I can find it many different ways. This is just a second way that you could do it. So here are 2 equations that I could add up to get to this equation that I want. And I have a delta G given for each one of these. So what I'm going to do is I have to look at, I have CO2 over here on the right. Which one has CO2? This one does. So I think I'm just going to keep that reaction the same. But I look here and CO, carbon monoxide, is over here on the reactant. So I'm probably going to have to flip this reaction. And this one, because I have two CO2s, I'm probably going to have to multiply this one by 2. So again, this is just like Hess's law. You just have to learn to look at it and see what it is. I'm going to pause the video here for a second. All right, so I paused it, and all I did was I wrote this first equation up here, down here. I flipped it. So I changed the sign of the delta G to a positive 1088. The second equation, I multiplied everything by 2, and I'm going to double the delta G here as well. So 2 times negative 801. So then I'm going to see if I could cancel things out. So I have 2 CH4s on both sides here. I got 4 oxygen, 3 oxygen, so really I got 1 oxygen here. I got 4 waters, 4 waters. I got CO2, CO, 2 COs, 2 CO2. So I think I'm ready. So 2 CO plus O2 goes to 2 CO2, which is exactly what I'm looking for. And then all I do is add the delta G. So delta G comes out to be a negative 514 kilojoules. And so, is this reaction spontaneous? Yes, it is spontaneous because it is a negative sign, So that's the second way you could do a delta G. So let's talk about the third way. So we could actually do essentially heat of formation, if you remember that. Same kind of idea here. So I have a table here of delta G. So they are in the third column on your formula sheet. Please recognize that delta G's for elements, just like delta H that we talked about, are a delta G of 0, okay? Because the change in free energy is always looking at from 1 mole of a substance from its standard states. So what that means is, okay, elements, their delta G is equal to 0. Okay, so all elements, so it's only the forming of compounds that we're talking about, okay? So we can do a third way of finding a delta G is by taking the products minus the reactants and, again, the number of moles that you have. So the F here is the forming of the compound. So just like we had the delta H of formation, same kind of idea. So this is okay. You could do this method if you have the table or if you have the individual G's, individual free energies of each one of the substances that you have in the balanced chemical equation. So this is what I call the third way of finding the delta G under standard conditions. So if I give you a problem like this, and I give you the delta G's, or I give you access to the table, you could do the delta G this way. So there's going to be sometimes I'm going to ask you to do it one way versus the other, just so you get the practice. But it really, since it's independent of path, it doesn't matter which way you do it. So again, please recognize that the H2 here is 0, so sometimes I might not give you the ones that are elements. So what are my products? I got my CO, which is negative 137. This is kilojoules per mole. And of course, it's multiplied by 1 mole. Plus, I have my water, which is negative 229 kilojoules per mole. Okay, so those are my 2 products. And I'm going to subtract from it my reactants. Well, I don't have H2, but I do have CO2. So that's going to be negative 394 kilojoules per mole. So please recognize that these are in kilojoules from the table. So negative 137 and a negative 120, negative 229 minus, and then this becomes positive. So the delta G here comes out to be a positive 28 kilojoules. So no, it is not spontaneous because of the fact that the delta G happens to be a positive value. So those are 3 different ways that you can find delta G. Just depends upon what the data that you are given in the problem.